common, and I just want to welcome all of you and thank you for coming. We're real excited about hearing what this study has done, and with that I'm just going to turn it over to Dr. John Richter, the President of Friends of the Jordan River, so he can do a more formal introduction.
Thank you, Ann. Ann's been the project manager for this little research project for, I was looking back this morning, since 2007. Actually, it started in 2006. Friends of the Jordan had generated kind of a white paper and sort of sent it out, posing some questions about the sand bed load in the Jordan River. And most of you are aware, you know, it's a sort of a conundrum. You know, we've spent enormous time trying to repair damaged sites and revegetating and fixing road stream crossings, and yet the sand persists and continues to sort of fill up the river. And you know, the more we studied it and asked around, everybody has an opinion, but when you're going to research literature, no one has any facts. And I was surprised to find that even worldwide, this type of an issue has never really been studied in a scientific way. And that's kind of the purpose of this meeting, is to, you know, kind of bring us up to speed and show everybody where we're at and what we found out and where we might go from here. So I have the great pleasure of having worked with Anthony here and Dr. Hyman and Dr. Kendall, excuse me. And maybe you can introduce the rest of your staff.
Sure, absolutely. There's several names listed up here. So I'm Anthony Kendall. I got my PhD with Dr. Hyman back in 2009. Sherry Martin wasn't able to be here today. She's another postdoc in our lab, Dr. Martin. She's been working on the project since 2010, so the last 18 months or so. Brianna Jasinski is here. She's an undergraduate researcher in our research lab, and she's been focusing her efforts on examining the role of beavers in sediment accumulation in the upper and middle portions of the channel. Dr. Van Dam was very active earlier in the project when we were using geophysical tools to examine the lower portions of the river where the Jordan River flows into Lake Charlevoix, which we originally thought was a delta. After geophysical examinations using tools like ground penetrating radar and just taking borings with hand augers, we decided that it really wasn't a delta. In fact, that the Jordan River didn't have a proper delta, which I'll bring up later. And I'll mention a few of his slides now, but as John mentioned, this has been a project that's gone on for several years. We've had all kinds of efforts in the field and back in the lab and in our computer labs as well. And this doesn't present all of that work here today. It presents the top of the pyramid. And then, of course, Warren was instrumental in getting the whole project going, and a lot of the discussions related to just some of the conceptual ideas for how to understand how the watershed had changed to allow its characteristics, the characteristics of the channel, to change so much. So I'll mention that we approached this problem initially from the angle of trying to understand it from the mouth. We would understand what the river had dumped into Lake Charlevoix. And in doing so, we would try and understand something about its history. And we pursued that angle and found that our initial hypotheses about how the river was behaving were incorrect. And the more we dug into it, the more we realized how that we needed to approach the river from a very holistic view, from looking at not just its surface watershed, but also its ground watershed. Looking and trying to understand all of the water that flows into the river. And through that, gain an understanding of how it's changed in the past, and how that's relevant in terms of trying to understand how we might affect the direction of the sand bed load and other types of issues related to sediment accumulation today. So I'll just make this statement off the bat, and this is really what we're interested in, right? That sand may be impacting the fishery. We've got a nice little illustration here of a whole, Teddy Kotowicz was a guide on the Jordan River probably from 1940 through the 1980s and even maybe early 1990s. And the Jordan River was renowned for its trout fishery, and people came from all over the state to fish on it. We have a picture of one of our collaborators from the U.S. Army Corps here. He just caught, a 2-inch fish, and just as a nice comment. He was out with us one day and threw his fly in wherever he could find a pool. And so anyway, it's not really meant to say that the fisheries declined that much, just to say that that's the concern. And so this led to funding of what I label as a 4-year effort, but is really, I guess, more of a 5 or perhaps even plus effort. So the talk outline today, first I'm going to discuss the project objectives that we originally set out with. And I will address most of those directly, but all of them at least a little bit here. There's 7 of those. And then the question is, where's the sand coming from? So we really need to understand the Jordan River channel. The whole watershed is the next bit of our focus here. We're looking at monitoring flows across the watershed, which we've been doing since 2008, and also doing computer simulations of how the watershed behaves. How after snow and rain fall on the watershed, how the plants take up that water, how some of it moves into the groundwater and then through to the Jordan River. And all along I'll be talking about some of the aspects of this river that make it rather exceptional, and it really truly is. If you look at all of the rivers across the United States, the Jordan River is one of the most stable in terms of its flows, which means that the difference between typical flows in the summer and the fall and the winter are very, very minimal. And it responds only slightly to rain events. A flood on the Jordan River might be something that is 5 or 6 times larger than a typical flow. A flood on a river down south in Michigan might be something that's 20 or 40 times larger than a typical flow. So the Jordan River is an incredibly stable river. And that gives us some really interesting behaviors that we really need to understand. The lower channel, so then we'll break, we'll have a chance for people to mull over what we've talked about, ask questions, get some refreshments, and then we'll come back. And then I'm going to break the channel into 3 segments. The lower channel, which is really the navigable section of the channel, really from Graves down. It actually extends, Graves Crossing down, it extends a little bit up from there. And there's a mechanism active in the lower channel that is different than what's active in the other channels, and that's that the lower channel is responding to lake level fluctuation. And I'll be discussing sediment transport modeling that we're in the process of, that we've recently started. I forgot to mention one of our names was not on the list. Travis Dahl just joined us from the U.S. Army Corps of Engineers. He's getting his PhD with us. He started in July, and he's actually doing our sediment transport modeling, and he's brought an enormous amount of expertise to bear in this project. So I'm going to discuss the lower channel and how it's different than the middle channel, where what we're looking at in the middle channel is not necessarily the movement of sand as much as the accumulation of sand due to large woody debris and beaver activity. And then in the upper channel, I'm going to discuss the impacts of irrigated potato farming. And it's something that has really exploded in not actually in the Jordan River watershed, but within its ground watershed. And I'll make that distinction clear and help you all understand how seeing the difference between what is sort of a traditional management boundary of the watershed and actually its ground watershed, which includes all of its contributing waters, that difference is really important here. And then we'll discuss summary and conclusions after that. So the research objectives, and I'll go through these kind of quickly, are what did the pre-development channel look like and what were its characteristics? We did a fair amount of work on this, not all of which I'll present today, but I'll make reference to this in a lot of different cases. The second one is what was the rate of sediment movement through this system, upper versus lower? And that's a problem that we're still looking at between today and when our final report is due, is pinning numbers down on that with sediment transport models. And then transport at different flow rates, how much bed load, and what is the stream potential. Has the amount of bed load transport been affected by development? That's something that we've looked at with our computer simulations, and I'll discuss. What are the origins of the sediments? A critical question, and one that we have a couple different things to look at. What can the sediments tell us about the past? Originally we had envisioned collecting sediment samples and then getting them dated with various methods. I should say, putting a date to when those sediments were deposited. And we collected cores to do that, and we investigated a technique called optically stimulated luminescence. But we never pursued it to getting a sample getting measurements because it's quite expensive, and we didn't think that it would actually answer the questions we wanted. So part of what you'll see, and I've already mentioned it with the idea that the Jordan River we thought it originally had a delta, and then it turns out that it doesn't really have a delta. That we've, in the process of trying to understand this, we've followed a hypothesis to a conclusion, and in some cases it hasn't been what we've expected, and so we've moved in a different direction. Did a natural or stable river ever exist? Did a gravel bottom river exist some time period, pre-development to 1800s, or pre-development or 1800s? And can potential human impacts be reversed? And this is, of course, a really big question, and one that has an interesting answer. And yes, we think the answer is yes, that there was an actual stable river system. And what could a future state of the system be under different management? And that's something that's sort of a soft target. It's more of what tools do we have, and how might we affect the state of the system with those tools? And that's something that we'd also like to discuss with you here today. I want to mention before I go any further that we created a survey. And one of the reasons that we did this survey was that there are not a lot of hard documented historical evidence on the state of the Jordan River from any scientific sources, government, agencies, or research institutions. And so what we thought was we could ask people who use the river every season. Maybe they come up here, take a vacation, maybe they float it in a canoe, maybe they wade part of it in fly fish, that type of thing. And we'd ask them, and we'd get their recollections of how they used the river, and then what the river was like when they used it. How might it have changed over the years? How might is there more algae than there was? Are the river levels higher than they seem to be in the past? Is the conditions of the bed different? Were they gravelly before? Are they sandy now? So far we've had limited participation. We did try advertising this in local papers. So if you guys are interested and you're users of the Jordan River, please visit this address. It's a little bit faint here, but it's just the FOJ website, friendsofthejordan.org/survey, and it's on their main page too. And also we're very interested in historical photos of the river. We've gotten a whole bunch of them from John. He had obtained a cache of them from the Kotowich family, right? As well as a few other sources. And those have actually been really, really helpful to getting a perspective, especially on the middle channel, because the middle Jordan was a puzzle to us for quite a while. We did numerous, so here I'll get started on some of the work that we've done. We've done numerous surveys of channel characteristics, which we've done via just floating the navigable portion. And one of the primary activities in that is we've taken extensive photographic documentation of the channel. We purchased a couple of cameras that have built-in GPS antennas on them. Every time you snap a picture, it tags it with the coordinates, and we can lay those out on a map and look at them to see how the river actually looks. And some of the things about that are very interesting. For instance, the river actually has gravel in a lot of places, and I should say gravel, and I'll explain what I mean by the quotations in just a second, because it's not what you would normally think of as gravel. And there are a lot of segments along the river where there's nice pools and there's good habitat for fish. So the images were also helpful in helping us to understand what sediment sources were. Initially on the first float we had the idea that perhaps there was some significant cut bank erosion. Cut bank is when a river that meanders around in its floodplain starts to move out toward one of its banks, it cuts it, and the bank actually gets quite steep and is depositing sediment into the river. If you've floated rivers around the area, you'll know that this is actually a fairly common phenomenon, especially in areas like the Jordan River that have fairly steep valleys, and the upper Jordan in particular. We didn't actually find any cut bank erosion, and so what we found in terms of sources of erosion for sediment were things that were a little more subtle. They were undercut banks, where the bank was protected by vegetation, but the water had flown under a little bit, which means that in recent past, in the lifetime of that vegetation, the river had actually excavated some of that sediment and moved it further downstream. We're working on getting these GPS coordinates finalized, and then we're going to put a link up on the FOJ website for browsing these, because it's actually really cool to see these just hundreds and hundreds of images, and we'll trim them down a little bit, just laid out on a map to see what the Jordan River looks like. And it's a really interesting way of seeing the river, because through photographs we can see things that we don't normally observe, maybe as we're floating and trying to avoid an obstacle. So the basic question, where's the sand coming from? Well, sort of the easy answer, but the obvious and correct answer is the sand is coming from the channel. A sand bed channel moves sand. Okay? So the Jordan River, in its current state, is capable of moving a sand bed load, which means that it has enough flow to push sand along the bed. So the sand doesn't become suspended up into the river It's not through turbulent forces or things like that. It's just friction of the water moving along the sand, along the bed, is able to push along this bed load of sand. And you can see this, it's especially active in the lower channel, near the mouth or near the boardwalk where the Friends of the Jordan facility is, that the channel gets very shallow and you can see all the bed load forms. And if you disturb them, you can see them form again. So the river is capable of moving sand. And so this is a shot here of there's a sand trap on it might be Penny Bridge Road or Jordan River Road up in that direction. And the sand trap was active during the 90s and early 2000s, and every year they pulled out about 1,000 cubic yards of sediment is what I've heard. And so it was quite an active sand trap. The function of it was to trap sand and remove it from the system, and it was later trucked out. Now it's completely full, and we visited it, and we did some floating ground penetrating radar studies where we actually floated a radar across the sand trap and imaged the bottom of the sand trap to see how full it had been. And this is it's sort of a trivial use of it, but it confirmed things that John had told us, which is that there were almost boulder-sized cobbles at the bottom of this sand trap that were remnants of perhaps an earlier channel. So bank erosion, as I mentioned, the channel is mostly vegetated along its entire length, and vegetated with things that have woody roots. That's the real critical factor here. Grasses are not as effective at armoring a bank because their roots are softer. There's some exposed soil near the water's edge. You see things like this occasionally. These vary a little bit by season. Like this can depend, whether this is visible depends on vegetation. But this is an incredibly common site along rivers, and there's really not that much of it along the Jordan River, along the navigable portion. So it's a very stable channel. And the stability of the channel is something that's a little bit exceptional. As I mentioned, the Jordan River doesn't really flood. And so very few times does the Jordan River actually get up onto its floodplain. And when it does so, it has very little power to actually scour away its banks. So its banks are mostly vegetated, and thus they're fairly stable. And so that's actually that tells us a little bit about where the sand is coming from. It's coming from down-cutting the channel and undercutting those banks. And in this, we'll note that this was possibly due to a recent high flow event. In April, we had a relatively high flow event for the Jordan River. I think it was the Project High, actually, since 2007. However, this is likely not a significant contributor of sediment overall, due to the bank erosion itself, due to the back-of-the-envelope calculation on how much sediment could actually be supplied. Travis recently took these photos. He went up and did some coring with a hand auger and collected some soil samples just in the floodplain, just out of the channel, at Old State Road in Graves Crossing. And basically what he found is that there's about 3 feet of organic soil with little to no floodplain sand, which is, again, this is something you would expect would happen in a river that has not pushed sand up over its banks in a very long time. And that there were no gravel or concretions, and I'll explain these concretions in just a minute. So this was fairly fine-textured organic soil that had just formed from the deposition of leaves and their decay over the years. And then also further downstream, or upstream I should say, at Graves Crossing, about 1.5 feet of organic soil on top of sand, and including some buried wood, so things that were relatively intact, but no sand. So this is evidence that the channel, we know it doesn't flood now, at least it doesn't leave its banks very often, and it hasn't done so in a while, because we don't have what you normally find on bank deposits, which is sand mixed in with finer textured materials. There's an interesting find a little bit further down the road, and this is the river. This is an image showing about a half-foot clay layer on top of sand, and then there's some organic soil on top of that. And this clay layer had some small snail shells in it. This is located at it's visible at the confluence of Deer Creek and Jordan River, which is only about 1.5 miles from the mouth. And I'll show you that on a map. I constructed this gold point here, shows this confluence location. What I did was I took, on the right is the lake level today. So it's actually 176 meters is the lake level. And you can see the lake right here, goes up to the bridge, and then it comes up a little bit further. So this is a relatively low lake stand. This is near historical lows. And If instead we look at the level of Lake Charlevoix prior to the dredging of what's sometimes called the Charlevoix River, or also called the Pine River in different references, but originally Lake Charlevoix was separated from Lake Michigan. Its level was slightly higher, and historical accounts put it about 4 feet. So if we take that 4 feet and we put it on top of what were higher lake levels already back in the past, we get that there was about a 2.5 meter difference. So a little bit over 7 feet of difference between the historical Lake Charlevoix level and the modern Lake Charlevoix, well, the modern low stand of the Lake Charlevoix, I should say. And so what I did was I just took our digital elevation map, which is just, and I'll actually show you later, it's a map of the elevations of the surface at every point, and I colored everything blue up to 178.5 meters, and what it shows is that the lake actually proceeded, or the surface of the lake actually continued right up until that confluence point. So finding these lake clay deposits at that confluence location is confirmed based on what is a reasonable estimate of the lake level prior to dredging. So we know that Lake Charlevoix was likely higher. There's something we also know about Lake Charlevoix because it wasn't connected to the Great Lakes, which can fluctuate actually quite a bit, 3 feet in just a matter of years. Its level was likely much more stable. That's really important for a river, and I'll show you a little bit more of this in a bit. But a river will cut down to what's called its base level, where it can erode no further. And its base level, the base level of the Jordan River, is whatever the level of Lake Charlevoix is. So if historically we had a relatively stable Lake Charlevoix that was separated by 7 feet from the oscillations on the Great Lakes, then the Jordan River had a chance to evolve a much more stable condition. And this is a condition that I'll continue to describe, but basically it's a condition where you have vegetatively armored or protected banks, and a river that doesn't flood, which means that the only way the river can evolve and transport sand, which it wants to do, is by cutting down. And there were some really interesting processes going on that actually armored the bed of the river itself. And we've got some suggestive evidence for this, but nothing that's just totally smoking gun yet. But I'll discuss that a little bit more, and I'm pretty excited about it. So you can see this process happening today. So looking at the bed composition, we have something called vegetative armoring, which is that this is a clump of sand. Here's a bunch of clumps of sand, and they are covered by algae. Well, you don't really get a clump of sand, like the algae aren't moving the sand, right? They're either trapping the sand as it comes in, or they formed on top of a higher level of sand that then eroded down. So this clump of sand is protected by this algae mat. Now, what this algae will actually do, there's one of the things about a groundwater-fed river like the Jordan River in this area is that it carries a lot of calcium carbonate dissolved in it. And that calcium carbonate, all it takes is a little bit of a change in the pH of the water, or what's called the redox potential, in order for that calcium carbonate to leave the solution in the water and form hard minerals. Okay? Those hard minerals will essentially, they'll deposit around anything that they can start on, a sand grain or a bit of algae. And then that will serve as a catalyst for more deposition of calcium carbonate from the water. And what you get is you get the formation of concretions. And these concretions are relatively weak. If you pick them up from the channel bottom, you can split them in half, and I've got a picture of that in a minute. And I've been talking to some colleagues around Michigan State, and one of them suggested that, from a colleague of his, this is kind of, third-party scientific hypothesis here, but that this type of vegetative armoring and leading to these calcium carbonate deposits was common, if not ubiquitous, across northern Michigan. And so an armored bed, a river that can't flood its banks, and a stable base level means that the Jordan River had a chance to form something of a relatively deep river in terms of from its banks to its bottom. And while it was not necessarily moving more water than it does today, and I'll discuss that in another couple of slides, it was a stable river in ways that perhaps prohibited moving sand. So there was no sand being liberated because the banks and the bed were armored. So we set out, so the first float we did was in 2009. It was raining, it was a cold day in October, and this was just our first attempt my first attempt, this is when I joined the project, at trying to understand what does the bed actually look like. And we saw gravel all over the place. And so we went back and we reported to our research group, well, there's gravel all over, there's sand all over, it's a mixture of gravel and sand. And so we said, okay, that's interesting. So there's this gravel, where did it come from? Because the material around, the uplands don't have gravel in them. They're very, very sandy materials. So then when we went back in 2010, we started picking up some of these gravel-sized things, and we said, okay, this looks like gravel, it feels like gravel, but you can split it in half. And it's called a friable material in geological science. But basically, if you can take a rock and you can split it in half, it's not a rock. And this is something which is really interesting, because if we think about the historical change that the Jordan River has observed, it has gone through an intense period of logging where the river was used as a transportation mechanism, as a highway for logs. And these things jammed into all the banks, and they piled up on top of each other, and the river forced them scraping along the bottom. And if you have an armored bed of gravel that has formed over millennia, the river's probably going to be reasonably able to withstand that. You're going to disturb it in places, and that's going to cause some problems. But on the other hand, if your gravel was never really gravel, but it was this relatively light stuff made out of something that you can break with your own two hands, then this disturbance by human activity is much more damaging. And so I make an analogy in discussing this, that when you step out on a tundra, you have this really interesting tundra environment, absolutely covered in plants, and you think, well, this is amazing that this lush vegetation can survive. But as soon as you step on that tundra, you create a disturbance that it takes a very long time to heal from. And if you have a lot of people stepping on that, or you're rolling logs across it, you're rapidly going to turn that tundra into a muddy, just absolute mess of melted permafrost. And so that is what we think happened in the Jordan River, at least along portions of it where these rocky concretions are present today. I'll note another thing about this, that the bed continued to be gravel, and there continues to be this gravel today. And this is actually relevant in terms of trying to understand how you might manage it. When you step on these things, they break. So if you want gravel in your bed, then you probably don't want to step on these things. I mean, it's not like they're completely just, you don't, but if you step on them really hard, and they press up against something else, they will break. So perhaps thinking of the channel itself as something which maybe needs a little bit more protection, maybe an angle to take. But the concretions certainly look like rocky gravel. And viewed all together like that, it's pretty much indistinguishable from a bunch of river stones that you might see anywhere in a high gradient stream in the Bighorn Mountains in Idaho or something. We have little evidence for historical sand transport, and I'll get into our geophysical evidence in just a second, but in addition to this, numerous anecdotal reports of a gravel bottom, which suggests that sand was being transported, or at least not being transported, or at least not in significant quantities to accumulate. We also have evidence from our coring and geophysics that I already mentioned that support this, and that I already discussed this as well, that many pre-development northern Michigan rivers may have been armored by calcium carbonate concretions and algae. I'll say another thing about these concretions. Some of them have layers of algae and calcium carbonate, like they've formed over the years. And so we're kind of interested in trying to figure out how we might take this interesting set of rings that you see in an exposed concretion and try to understand what was its formation history. How long did this thing take to form? Is it, are we looking at like 1,000 years here, or is it 20? I think that has very different consequences in terms of trying to understand how might we return the river to something more resembling its initial state, or at least its state prior to our use of it. So, starting back in 2006, maybe late 2006, early 2007, Remke Van Dam and a master's student at the time, Chris May, went to this delta. And what this is where the Jordan River flows into Lake Charlevoix. So here's the highway and the bridge. And took numerous different samples in a couple of different campaigns. They did some ground penetrating radar work in the wintertime where they towed with a snowmobile, they towed the GPR with its radar antennas on sleds across the delta. And what they found were things that don't look like a delta. They look like regular, just regular deposits that were left over by some other process where there had been some lake sediments falling on top of that, as opposed to layers of sand where a channel meanders around, it deposits sand here, and then this gets too high, so it flows over here and it deposits some more sand, which is, and I meant to put a picture in here, which you can see today if you look at Google Earth or Google Maps and you look at Patricia Lake, which is on Deer Creek just above the dam. You can see a sand delta. So clearly, if Deer Creek can put a sand delta into Patricia Lake, the Jordan River could put one into Lake Charlevoix, but it didn't. And so this is really interesting and suggestive evidence to us. We also did, and this slide maybe just slightly ahead of itself, but it supports the idea that there was a river bottom that is not now what we see today. So we took our ground-penetrating radar instrument, and we put it on a boat, and we floated it across the channel at the Webster Bridge Gauge location. And this is a ground-penetrating radar view. It looks a lot like seismic images, if you've ever seen these from the oil exploration industry. And what this shows is the bottom of the river. Okay, so you get all these little color variations are when you get some sort of reflection or the signal that the antennas receive, that they've sent a radar wave down and received it back. It has some fluctuation in it. And so there's a strong reflection going on here, and then potentially something going on deeper down. And so this is, I'm not the geophysicist on the project, I'm just reporting his results. And basically, the 250 megahertz, so we have two different frequencies. A higher frequency has more resolution, but it doesn't go as far into the sediment. So our 250 megahertz suggests that there's a deeper paleo channel, or a previous channel, what would have been the exposed channel at an earlier point in time, that's about 0.6 meters down beneath this. So 60 centimeters, something on the order of 2 feet down beneath the Webster gauge. And so we haven't done any coring. We investigated various techniques for doing coring and decided them not really worth exploring for what we needed to find out at this location. I'll talk more about what's going on at the Webster gauge in subsequent slides because it's really quite interesting. But this is, if we explored this particular avenue further, what we might find, what we suspect we would find, is that there is a channel bottom that was formed at an earlier point in time that was then buried by sand and gravel, these concretions, which is now the current channel bottom that we observe today. But what we don't know is whether that channel bottom was in fact the channel bottom pre-development. That's just a different view. Oh, here's the interpretation. Okay, so that is our characterization of the channel, at least the lower portion of the channel. I'll talk more about the upper channel after the break. So the history of the Jordan River is really characterized by logging. It was, prior to around 1870, it was covered by a whole variety of species, including cedars and white pine, and some maples and oak, things like that. They were commercially valuable. And so these were logged intensively. There were railroads built along the Jordan River Valley. There are remnants of graded railways still today that cross at various points. There were bridges built. All sorts of disturbance activities were done. So peak logging occurred in around 1890, but logging continued of various species, sort of going down the value ladder, until about 1920 when logging ceased. So as the logging industry was relatively thriving, and there were other industries, including the ironworks going on in East Jordan, it required people to supply food. There were no interstate highways or even developed roadways of any kind, really, that could bring food from long distances. So people farmed what really are very marginal agricultural lands around the Jordan River Valley, or around the Jordan River. They're really only suited for growing one type of crop, and we'll talk about that in a little bit. And there other things are grown, but this is not, productive Iowa soil here that we're talking about, or Illinois soil. As soon as the logging industry ceased, and the economy of East Jordan shifted, marginal agriculture largely ceased. I mean, the people did subsistence agriculture, but that really declined. And as it declined, the state reclaimed a lot of the land that had been in agricultural production and pieced together elements or pieces of the Mackinac State Forest that weren't then left undisturbed. So here's an aerial photo image from 1938. And what it shows is a square segment that was mostly not logged. So there's the The river channel flows down the middle of this, right here. This was mostly left undisturbed, but everything around it was logged. I'll note about the Jordan River, it was mostly still, the swamp cedar that are in the Jordan River Valley today were mostly also left undisturbed. So it's actually a really beautiful place because these swamp cedar were not harvested, and so what you see are trees that are, in many cases, quite old as far as swamp cedars go, and I don't know exactly how old that is. So over from 1938 to 1973, there's a great deal of forest regrowth. They're expanding out into this open area, and then by 2005, this is a color image, but most of that open area is now filled, except for certain places. These are likely wetlands, places that will never really grow trees. So the Jordan River, the middle to upper Jordan River Valley, reforested steadily. And how that takes place is through a process that we call succession. And in early succession, what we see are shrub species or scrub species and bushes that actually grow first. We can also get fast-growing species like aspen and jack pine, particularly since jack pine are triggered by fire, which were fairly somewhat common at the time because they were only partly controlled in a relatively unpopulated section of the Jordan River Valley. After these initial species grow and they start to die, they grow quickly, but they don't live very long. The second and third growth trees and different parts of the forest ecosystem, vegetative ecosystem, take hold. And so today what we see in the Jordan River Valley is really a fairly mature, but still maturing forest with a whole variety of different tree species. These aspen are very important because the beaver really like to eat them. And so we'll talk more about beaver. So one of the activities that we've been doing since 2007 is monitoring flows in the watershed, stream flows. The USGS has maintained a gauge at Webster Bridge since 1966, and we added in 2007, we added one on Deer Creek. This is Patricia Lake that I mentioned earlier. We added one at Graves Crossing, and then we added one just upstream of the fishery that we call fisheries. And we've been monitoring those. I'll show you the flows for those in a second. Right. And we also measured flows at dozens of other locations across the watershed. So I'm going to go through these just to give you an idea of how we do this, a little bit of the sort of sausage making of science. This is our Deer Creek site at Richards Road. What we do is we install an instrument in the stream channel. The instrument measures the level of the water, the height of the water above the instrument, according to the water pressure, and it measures the temperature of the water every so often. We set it at about 30 minutes in our instruments. And what we need to do then, so we've got the level of the water, we actually want to know how much water is flowing through the channel. So what we do is we use what's called a rating curve, where we measure the height of the water and then we measure the flow using a different instrument. And we develop a curve. So what we did, if you just look at the red points, was over a period of about a year and a half, we measured at 6 different times the height of the water and the flow in that system, and then we fit a curve to it. And this is a really great fit, actually. This is a measure of how good the fit is, and if it's 1, that's perfect, and this is 0.9921. So it's actually very, very good. It's an excellent rating curve. Well, there's people who live right here, and they wanted to enhance the aesthetic qualities of their lodging. And so what they did was they downed, actually very nicely, downed some logs in the stream and built this beautiful like stair-step cascade that backed up the water level to our gauge. And so then we needed to establish an entirely new rating curve. And so we were able to do that, and we also got a pretty good relationship. So we're pretty happy with the results of this one, and you can see, so we've got fairly continuous monitoring of flows since 2007. What we've done is we've blanked out periods where the gauge was actually frozen solid. And so this particular instrument can't measure the flow in a frozen river. So the river itself wasn't frozen, just the gauge. So, right, so this is the continuous record. It's fairly unexceptional, except I'll point out that the Deer Creek, because there's on the Deer Creek, there's a sizable lake upstream, and I don't know the name of that lake. Water falling on the lake actually provides a bigger response to precipitation or rain events than anywhere else along the Jordan River channel, or the Jordan River watershed. So what you see in the Deer Creek is a bigger response to rain events than you would see on the main channel itself. But overall, it is also a very stable flow system. Yeah?
That peak that
This peak right here, we're using an exponential curve, which these systems typically, they'll behave exponentially originally, and then they'll kind of level out.
You got off the relation.
This is an extrapolation. Yeah, exactly. I'm comfortable in this range, even up to the 150 range, since we have measurements up there. Right. So, exactly. So since we don't have measurements up there now, we actually made an attempt in April to do this, and we brought our fancy instrument, and we thought we were using it right, but we didn't use it. We didn't use it correctly. So it was a learning process for us, and next time there's a high flow event. The trouble is high flow in the Jordan River lasts about 16 hours. So if I live 3 hours away, we had to keep like a ready kit, and then just jump in the car and drive up. John would call us and be like, "Hey, you need to come up here. We've got high flows." So. The Jordan River site at Graves Crossing has had a much more stable relationship, I should say, a little bit less good of a relationship, and that's because what you see here is we didn't have our fancy boat called our ADCP for measuring flows. We had just a manual method where we wade through the channel and hold down a rod that measured the flow at each point, and then we had to sum those up. So we've got two different methods that mostly agree with each other, but because of methodological differences, there's a little bit of spread in the data. And so we have also very stable flows here. Again, this is something that's extrapolation outside the range of our measurements, but I'm comfortable with anything under the 400 range. So all of these peaks. What you see here on the main channel is this is rock steady. That this varies. It's 120 cubic feet per second plus or minus 10. You'll be within. You'll be within 10%, just sticking with that number. And then one more site, the fisheries site. This one we've had a little bit more trouble with the instrument, and we've lost some data. But we have a pretty good rating curve, only in recent times. So we've been working with that site. Smaller sites tend to be more problematic because they change through time, especially sites that have culverts that have been somewhat recently redone. The system is constantly sort of accommodating those. Okay, and then I'm going to make one more comment about the Webster gauge. This is, to most of you, it probably looks rather unexceptional. So this is a 3-year period of record, and over this period of record, what you see is in the winter and early spring, you have a tendency toward higher flows. They get lower in the summertime. In a system down even in, say, Muskegon, the Muskegon River, or around Houghton Lake, this value, 150, might go up to 600 in the spring. So it would go up by 3 or 4 times in the spring, whereas it goes up from 150 to 180. And that really makes it a very interesting system because it just behaves very differently. It actually, from trying to understand how streams evolve, a stream, say the Mississippi, will flood really massively every once in a while. And in the process, it'll say, well, I've just found a shorter path than I was flowing in before, because I'm flowing so high, so at such a high level, I can go over my banks, and hey, it turns out this is shorter. I'm going to cut right through and make a new channel. That's called avulsion. The Jordan River can't really avulse its channel. It's stuck. It's stuck in what it's got. And we tried to actually collect some photo evidence for this, but we were limited a little bit by the sophistication of the aerial photos and our ability to make the aerial photos match up precisely through time. Okay, so the last thing I want to talk about, oh, nope, there's some very interesting things here. Okay, so the Webster gauge has been operating since 1966. And so what we thought was, well, let's look at the minimum flows, the average flows, and the maximum flows annually, and just see what's happening to that gauge, or to that system. And what we see is there's almost nothing happening to the minimum and average flows. These trends of minus 1.7 cubic feet per second per decade, I mean, this is not a significant trend overall. So these are, average and minimum flows are not changing in the system. It's been steady over this period, which is actually this is fairly exceptional. Most of the streams around here have a steady increasing trend, and actually a significant increasing trend. And the peak flows have gone down very significantly. This linear trend kind of doesn't tell the right story though, because really after about 1996, this system behaves differently. So there's a spread with no trend to 1996, and then after that, it behaves differently. And we haven't really dug into that enough, but it's likely due to climate change. And by climate change, we don't necessarily mean human-induced anthropogenic global warming. as much as the climate is different, and it has been different for the last 15 years than what it was the prior 30. That's the observation here. And so we tried to understand, well, why might this decrease in maximum flows? What might be the cause of that? And I apologize if you can't really see this, but I'll explain it in words. So what I did was I took for each year, I said, well, what is the summer, spring, winter, and fall, or it is in order, winter, spring, summer, and fall, total flows, or average flows. And then I'll look at those as a percent of the annual. So, you know, if normally, in the fall, if you look at this, fall accounts for about 25% of annual flows, and that's not changing. So that says something about the Jordan River, that 1/4 of the months of the year account for 1/4 of the flow through the system. Summer is a little bit lower, and you'd expect that because the plants are using the water. But what's interesting, and there's no significant trend in summer or fall, but the winter has been accounting for an ever-increasing share of the annual flows. So winter, by winter I mean January, February, March, and the spring an ever-decreasing share. And we see this elsewhere too. And what this is caused by is it's caused by an earlier snow melt. Or if not an earlier final melt, an earlier preliminary melt, where you get a partial melt, say in February or in March, that leads to water that would have normally been locked up in the snowpack until late April being released. So this, as soon as it's released, it starts to percolate down through the ground. And what this would normally have done, and if I looked at it, I said, well, where are all these high flow events coming? They're coming in June mostly. So it takes a couple of months for that snowpack recharge, groundwater recharge, to percolate through the ground and then really hit the stream as a high flow event. And so something in the last 15 years has led to the snowpack melting earlier, or just melting a little bit more often, so that there's not as much left of it in the wintertime. And you'll have to take my word for it that the precip, the actual amount of snowfall, hasn't been changing that significantly. So it's not that there's less snow, it's just that the snow, when it melts, has changed. Yes?
Did you reach that conclusion because of the strong relationship between winter and spring?
Mm-hmm. Just that winter is increasing. So that the flow in January, February, March is increasing, which means that you must have had melt events in January and February. And the spring is decreasing, which means that those melt events that happen in in early spring, in mid to late April, are happening earlier. And that's really the causal relationship there. So that's really all I'm going to say about climate change. So climate change is something that we're very interested in as a research lab, and we've actually run our model for some climate change scenarios, but that's, I think we have enough on our hands without really venturing too deeply into that.